Alright guys, so in this video we are going to look into the difference of differentials. Alright, it's going to be a pretty short video, but let's dive in. So the question that's presented to start this video on off is, does the integral of f of u du equal the integral of f of u dx? Obviously the only blatant difference that we see here is that the du and the dx are different. Our differentials are different. The respects to are different in each case here. So we haven't dove too far into integrals yet. So let's relate it to something that we have dove into pretty strong in derivatives. So let me ask you a question. Let's say, for instance, I said you have a function f of x, also known as y. And let's say that I said find the derivative of f of x or the derivative of y. It would be true that this would be f prime of x would equal dy dx, the derivative of y with respect to x. So we read that dy dx, right? Alright, so now let's say, for instance, alright, we are looking specifically at another function, okay, in which I said find the derivative now of f of u that is equal to u, and I said find that derivative. Well, that would be f prime of u, which is equal to du. Now, let's look at the two options that we have here. One is of y with respect to x, one with of u with respect to u as well. Those are obviously going to be completely different scenarios. Those will not be equal derivatives in this case. You are showing a different with respect to, or a different differential when it is all said and done. So, to answer the question, no, it does not equal one another. And in fact, because they don't equal one another, we're going to use it to our advantage to use what was called substitution, a u substitution, as a way to integrate. Before we get there, I got an example in this video that I want to look into as to really showing the importance of the difference of the differentials. So let's take a look. The example is as follows. Let f of x equal x cubed plus 1, and then you're going to let u equaling x squared. It wants to find each antiderivative for the following three cases. F of x dx, f of u du, and then f of u dx. So I am taking the integral of a function of x, y, right, with respect to its independent variable, x, okay? So, with this particular case, what this is showing is we'll call fy for a sec. Y is your dependent variable, x is your independent variable, because whatever happens to y is contingent on the value of x itself. So I will take the antiderivative of y, or f, with respects to the independent variable x, okay? So how could this possibly look in this particular case here? So if I'm going to go ahead and be taking this, we know that f of x in our example was x cubed plus 1 dx. Normal integral function, so we take it with respect to x. That means we will raise the power, divide by the new power, and when it's all said and done, we have our integral, or constant of integration here. Everything's copacetic, good to rock and roll, no big deal. Alright, let's move on down to the next one where we start kind of changing some things up a little bit. Now let's say, for instance, we have the integral f of u du. Well, alright. If f of x equals x cubed plus 1, that means that we are going to be dealing with f of u being u cubed plus 1, right? That is our fundamental theorem of calculus working at its finest. So if f of x is x cubed plus 1, we just flop out the u and the x, and now this is the same thing as x, or u cubed plus 1 du. Alright? And now taking this, we have u to the fourth, oops, get rid of this, All right, u to the 4th over 4 plus u plus our constant of integration. Okay, so far it doesn't look any different. However, all right, this is in terms of u, but u has value. U is x squared. So, in this case, we will have to replace what u has value for. And so if u is x squared being raised to the 4th power over 4 plus x squared plus c really makes this x to the 8th over 4 plus x squared plus c. So, let's kind of compare the two. A, f of x dx, gave us x to the 4th over 4 plus x plus c. B, f of u du, looks like the same scenario happening. The independent variable u, the differential u, why is this different? Because u had a different goal in mind. U had a goal of equaling x squared. So we have to take that into account when we are taking integrals. And this is where our fundamental theory of calculus comes on into play in an example like this. Now, let's move on down to our last one. F of u dx. Well, now, once again, we are going to be looking on into taking u as a notion with the fundamental theory of calculus that really, all right, this is f of x cubed plus 1, which is really f of u cubed plus 1. So, this will be u cubed plus 1, but now we are taking it with respects to dx. So, I am taking a differential of dx, but I have a u in my integrand. Problem. Not possible. We have to utilize what u equals to go ahead and say that if u is x squared, this is x squared to the 3rd power plus 1. Now, variable x, differential dx. Now we're in motion here. So now I have x to the 7th over 7 plus x plus c when it's all said and done. Notice the difference between each of the 3 scenarios and what happens. The reason why we change out the u and the x is so we can use the fundamental theory of calculus. But notice how it happens here. You cannot take the integral of f of u if your differential is with respects to x. That's not possible. You have to make sure that they match up, that the u, the independent variable inside of the function, and the differential match up so they are the exact same thing. This is going to help us on out when we dive into u substitution as a way of integration here. On to the next one, folks.